Hello and welcome to this IB Maths Intense video. This is the first video in a set on the subject of exponentials and logarithms, part of the topic number 1, number and algebra. And in this video we'll be just revising really the laws of exponentials so that we've all got the same basic knowledge going forward. This is in the syllabus as SL 1.5 and SL 1.7. There you are, you can see them there. And laws of exponents with integer exponents and laws of exponents with rational exponents. I know some of you will have seen this before in your prior learning, but it's important that you have got mastery of this topic. None of the formulae, laws of exponentials, are on the formula sheet, so this is something you need to make sure you fully understand and have learned. So without further ado, what do we need to know? Well, a bit of terminology. You're used to seeing expressions of the form a to the power of n. Hopefully you know that a is referred to as the base here, the base, and the n at the top is often referred to as the exponent or the power or the index. So this is a great mathematical shorthand, 5 to the power of 17. We don't want to have to write that lots of times. A to the power of n, back up here, of course we know is shorthand for a times a times a times ... times a n times. So 5 to the power of 17 is 5 multiplied by itself 17 times. So very useful shorthand, and you'll see it a lot. Just a word of note about negative bases, because of course as well as 5 to the power of 17 we could have had minus 5 to the 17. It's fine to have a negative base. So just a little bit about the behaviour of numbers with negative bases. Let's use a simple example. If I had negative 2 squared, we know that minus 2 times minus 2 is equal to plus 4. It gives a positive solution. If I had minus 2 to the power of 3, however, I'd have minus 2 times minus 2, which gives me positive 4. But then I'm going to multiply that by minus 2 again to get negative 8. So I get a negative solution. So in general, if I have a number, a negative number, and I raise it to the power of an even power, I will get a positive result. And if I have a negative number raised to an odd power, I will get a negative result. Very important, make sure that you remember that behavior. It's very useful, and people make silly mistakes all the way with that particular problem. Let's go to some laws of exponentials then, multiplying and dividing. If I had, for example, 2 squared times 2 cubed, I could write that out in full. 2 squared is 2 times 2, and then I'm multiplying that by 2 times 2 times 2, and so you'll see there I've ended up with 2 to the power of 5. But no prizes for seeing that that 5 is actually the result of adding together the two exponents. So 2 to the power of 2 times 2 to the power of 3 is 2 to the power of 2 plus 3, which is 2 to the power of 5. So generalizing, we know that if we have a to the power of m and we multiply it by a to the power of n, we will get a to the power of m plus n. An important result and one of our key laws of exponents. If we divide, we get a similar sort of setup. But if I had 2 to the power of 5 and I divided that by 2 to the power of 3, for example, I'm going to get 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. And I can cancel all of this down and I end up with just 2 times 2 on the top, which is 2 squared. Now again, hopefully you can see the link between the 2 there and the 5 and the 3 there. This time if I'm dividing, I subtract the indices. So as a general rule here, we can say a to the m divided by a to the n will give me a to the m minus n. So there's our second important law relating to multiplying and dividing. That last example does give us the opportunity to get a negative index from our result. So if I had 2 to the power of 2 divided by 2 to the power of 4, that would give me 2 times 2 over 2 times 2 times 2 times 2, and cancelling that down gives me 1 over 4, which is 1 over 2 squared. Now hopefully you can see there, I've got a 2 on the bottom, but hang on a minute, 2 minus 4, which was our result from before, would have given me a result of 2 to the 2 minus 4, which is our previous rule, gave me 2 to the minus 2. So we can see that 2 to the minus 2 is actually the same as 1 over 2 to the power of positive 2. So as a general rule then, a to the minus m is going to be 1 over a to the m. And that's another very useful result. Often it's easier to work with things in exponential form, a to the minus m, negative index form, or you might want it in fractional form so that you can cancel things down. They're both fine. Just make sure you know that that is an equivalent. And we could also bring in here that we can, of course, combine. So if we had a to the power of minus 5 times a to the power of 10, don't forget we're adding the indexes here. 10 plus minus 5 is 5. So the same rules apply with negative indices. Fractional indices. Here's an interesting idea. We know that we could, using the laws of indices, we could have a to the power of a half times a to the power of a half. And that would give us a result of a to the power of a half plus a half, which is a to the power of 1. Now, hopefully you know that two numbers multiplied together like that to give the result a must be the square root of a. So a to the power of a half is another way of writing the square root of a. And similarly, if I had a to the power of a third times a to the power of a third times a to the power of a third, my laws from before, adding the indices, that would also give me a. Which number do I multiply by itself 3 times to give a? Must be the cube root of a. So you can see the pattern now. And in general, if I had a to the power of 1 over m, that must be the mth root of a. That's an important result again. Now just combining a couple of the laws that we've seen so far, sometimes I could have a combination. So I might have, let's say I've got 8 to the power of 2/3. Now I'm not sure how to calculate that in my head, for example, but I can split that out and I could say, well, that's the same as 8 to the power of a third squared, which is equal to 2 squared, which equals 4. And you'll see where that comes from in a second. Because we can raise a power to a power. So if I had 2 to the power of 2 and I raised it to the power of 3, this is shorthand for saying 2 times 2 times 2 times 2 times 2 times 2. Now hopefully you can see this is 2 to the power of 6, and hopefully you can see the link between the 6 there and the 2 and the 3 there. This time I've multiplied the powers together. So 2 to the power of 2 times 3 equals 2 to the power of 6. As a general result then, a to the power of m raised to the power of n will always give me a to the power of m times n. Now, that's very useful. I could have 3 to the power of 6 to the power of 4. It's just going to be 3 to the power of 24. But in the earlier example, just on the previous slide, I showed you with a fraction. This is particularly useful for splitting things out. So if I had a to the power of 2/3, that can be split working backwards as a to the power of 1/3 squared. And that's really useful because often it's simpler to work with the two separated out if you want to evaluate something. So for example, 4 to the power of 3 over 2, We're not good at doing things to the power of 1.5, but that is the same as 4 to the power of a half, then cubed. And 4 to the power of a half is the square root of 4, which is 2. 2 to the power of 3 is 8. That's a lot easier if you split out the fraction like that, so that you can evaluate in 2 steps rather than 1. The power of a product, sometimes we have an expression where we've got two things multiplied together, so maybe AB, and we're raising it to the power of something, AB all cubed. We can think of it in the totality as all being cubed, but we can also split it out. This is A times B times A times B times A times B, which is the same as A cubed B cubed. So you can decide which is the best way to handle that expression, but they are both equivalent. So in general, A B to the M is the same as A to the M B to the M. Again, useful. And again, combining things from before. So let's say we had A squared B cubed, all raised to the power of 4. We can see that as, well, that would be A squared to the power of 4, B cubed to the power of 4, and then my other law from earlier gives me A to the 8, B to the 12, power of a power. So you hopefully can see that you can do that all in one go. 4 times 2 gives me my 8 over here, and 4 times 3 gives me my 12 there. And that's also a very useful and quick way of dealing with that expression. And then last but not least, the power of a quotient. So we could have an expression like A over B, all raised to the power of M. And like before, this can be simplified to A to the M over B to the M. They're both equivalent. So if I had 2 over 3 squared, that's equal to 2 squared over 3 squared, which is 4 over 9. So there's a nice rule to remember. And again, like before, if I happen to have an expression which had A squared over B cubed all to the power of 4, I can take each of those separately. That's A squared to the power of 4 over B cubed to the power of 4, which is A to the 8 over B to the 12. And again, hopefully you can see 2 times 4 gives me my 8 there, and 3 times 4 gives me my 12 there. Nice and straightforward. So I've gone through those really quickly, but it's good just to recap on the laws of exponentials. On this slide, here's a summary. Take a screenshot or write them down, or make sure you've got them somewhere so that you can learn them. There's a couple of extra results that I put in there just as a note. Make sure you remember that A to the power of 0, this one here, is equal to 1. Make sure that you also know that when you're dealing with negative indices, you can't have a value of A that's equal to 0 because you can't divide by 0. But there's a nice summary for you. Whilst you're still working with exponentials and you haven't mastered it, have those to hand so that you can refer to them. Great, we made it. Thank you for watching. Don't forget to like this video, subscribe to my YouTube channel, IB Maths Intense, tell your friends I'm here, and drop me an email at ibmathsintense@gmail.com if you've got any queries, requests, or if you've spotted any mistakes that I've made. In the meantime, it was good to have you here. Enjoy your maths and you take care.